Okay, continuing on with section 4.1, we're going to talk about something called the natural base e. And e is an irrational number, which is approximately 2.72, and is called the natural base. The function f of x equals e to the x is called the natural exponential function. The number e lies between 2 and 3, because 2.72 between 2 and 3. Again, it's approximately 2.72. It's really 2.7182281872. It goes on forever. It's kind of like the number pi, it goes on forever, but we say it's approximately 2.72. Okay? For more information on e, where it comes from, you can refer to your textbook or go into the multimedia library. But right now, I want you to go ahead and find the natural base e on your scientific calculator. If you purchase the TI-30X2S, the e button is 3 down on the left-hand side, but you have to hit second LN to get the e. So I get, it'll be this little button that looks like this. Look for that. It's the third one down on the left-hand side. So anyway, you're going to find that on your calculator. You type that in, and it'll give you then I'll give you that. So type in 1. But now actually we're going to type in 2. We're going to do e squared. So we're going to find that squared. And when you do that in the calculator, you'll get approximately 7.389056099. Okay. So let's go ahead and let's remember, let's go back to y equals 2 to the x and y equals 3 to the x. We did that before, and let's do it and compare e to the x. Okay, so I'm going to graph right now y equals 2 to the x. So 0, 1, because I'm graphing y equals 2 to the x. So 0, 1, I put 0 in here, I get 1 back out for this value here. Put 1 here, I get 2. So 1, 2. I put in 2 in here, I get 4, so I get 2, 4. I put in a negative 1 in here, I get 1 over 2 to the first, which is 1/2. So negative 1 will give me 1/2, which will be right there. If I type in negative 2 in here, it'll give me 1 over 2 squared, which is 1 over 4. So negative 2 will give me a 4, which is right there. Okay, and my horizontal asymptote is going to be the same. Well, that as before is a y equals 0. I just graphed here just y equals 2 to the x. I'm going to do that for a reason. We'll see in just a second why. Okay, this is y equals 2 to the x. Okay. Now if I want to graph y equals 3 to the x, I'll do that in blue. The first point is going to be 0, 1, which you should be the hypotenuse. 1, 3, and 2, 9, which I don't know for, but I'll go in forever there. I do negative 1, it should be 1/3. I do negative 2 would be 1/9. So, yeah. And the horizontal asymptote is still the same. So y equals 0. Let's go ahead and graph this. And that's 3 to the x. Now if I want to graph e to the x, well remember e is just 2.72 approximately. So I went ahead and found e squared, which is about 7.34 or 3/8, so about 7.4. So when e is 2, just in green, when e is 2, I get 7.4 approximately, and I can't fit that there. When e is 1, I get 2.72, so 1 and 2.72, here's 2.5, 2.72 right about there. When I put in 0, it'll be 1, get any number to the 0 power of 1. And so it looks like this is going to fall between those two graphs. And I do a negative 1, so 1 over 2.72, about 0.36, about 0.4. More than that though. But you notice how here I have in green y equals e to the x. That's going to be between 2 to the x and 3 to the x. That should make sense because e is 2.72. That's between 3 and 2, or 2 and 3. Okay. So let's go ahead and look at when we're going to use e. And we use e a lot when we talk about population growth. And so here I have an example. You can read through it. And it talks about how the gray wolf population were, I guess, close to extinction because they were being killed and shot and trapped and poisoned, and the population would reduce to 800. And then the population started to rebound after it was declared an endangered species and got federal protection, so it started to go back up in population. And with exponential functions, you might notice that in all the graphs we looked at previously, it shot up pretty quickly. Once you see the graph go up, it shoots up pretty quickly at a very fast rate. That happens with population growth a lot. Is when the population starts to recover, it just shoots up exponentially. So here is the function that models the population X years after 1978. And if the trend continues, we can project the population in 2010. Again, right now we're past 2010, but we can project the population in 2010, and we can actually project it in 2020, 2030, 40 if the species continue to reproduce and we're still on the endangered species list. Okay, so let's look at this function f of x equal 1.26 times e to the 0.247x. And we want to figure out the population in 2010. Well, x represents the years after 1978. So 2010 minus 1978 gives me 32. So x would be 32. So f of 32 equals 1.26 times e to 0.247 times 32. And I'm going to go ahead and replace this with 7.904. And then I'm going to type this on my calculator. 1.26 times e to the 7.904. And I get approximately 3,412.2. And so again, we're talking about population, so we can't have 0.2 of a wolf. So the population would be approximately 3,412 in 2010. So on your own, you do this one and the next one, and it says here to model the gray wolf population in 2012. Let's go ahead and go way to the future. Let's go ahead and do 2075. Way past my, who knows if I'll still be living back in that time, but way in the future. Let's say the gray wolf population is still on the endangered species list and everyone leaves them alone. If we continue this trend, what would the population be in 2075? So go ahead and do it on your own. I'll pause the video. You can check it. Okay, so this is on your own example. We were, the example we did a second ago, or with the northern Rocky Mountains, and here we're doing the population in the western Great Lakes. So it's a different model. That's why the model is different than this model right here. So different areas of the country. So again, in 2075, 97 years after 1978, I got about 62,671. I rounded up to 72. So the gray wolf population in the western Great Lakes would be approximately 62,672. Okay? And with that problem, I really wanted you to be able to use your E button comfortably. Okay, I'll be using that a little bit later on throughout this chapter. Okay, next thing we're talking about something called compound interest, and I know a lot of y'all deal with money. So this is a great way to look at a real life problem. Compound interest is the interest computed on your original investment as well as any accumulated interest. So when you put money in the bank, you get interest off of it for the most part, and a lot of times you'll get interest based on what you put in plus interest on your interest. So that's really interesting, and it works really well, and it uses a lot of these exponential functions. So let me go ahead and give you a formula, and I'll give you the formula on the exam. You don't have to memorize it, but we have to be able to use it. Okay, so let me go ahead and write A equals P times 1 plus R over N raised to the NT. And that is the compound interest formula. And A stands for accumulated interest. Or accumulated amount, not interest, accumulated amount. P stands for the principal. That's the amount you put in or borrow. So in the bank, you can either borrow money or you can put money in. That's the initial amount that you put in or borrow. N is, or R is the rate, the interest rate per year. It's percentage per year. And that is add the decimal. So if you have like 5% interest, it'd be 0.05. N stands for how many times it's compounded a year. And then T stands for the time in years. Put that in. So how long do you put that money in the bank in years, or how long do you borrow money in years? Okay, let's talk more about N. What does N mean? N means the number of times compounded a year. So N, the compounded N times a year. What that means is if it's semi-annually, then N equals 2. That happens twice a year. If it is quarterly, N equals 4. That happens 4 times a year. If it's monthly, N equals 12. That happens every month, so 12 times a year. And then daily, N equals 365 or 360. Now we know there's 365 days a year. Most time banks use 360 because it's just an easier number to use. But they say there's 360 days a year. Depending on what book you use or what bank you use, they'll use either one. I believe in our book we use a 360. Okay. Now there's something called compounding continuously. That means it compounds every trillionth of a second, so constantly compounding. And that formula is going to be A equals P e to the RT. Again, P stands for principal still. E is that value we talked about before. It's in your calculator. You can store that in your calculator. R is still your interest rate as a percentage, or interest rate percentage as a decimal, and T the time in years. This is continuous compounding. Every millionth or trillionth of a second. Again, computers will do that for you. And some people think, well, if you're constantly compounding every trillionth second, you might make more money this way. And that's not necessarily true. So we'll look at some examples in just the next part. So again, I'm running out of time right now. I have run up to my 15-minute time limit. So I'm going to go ahead and stop the video, and then we'll do some examples dealing with compound interest in the next part. The part 4 will deal with that.